Okay, so we're going to be looking at Module 3. Module 3 is about vectors. I am certain that in the coursework that you've done, not only in this program, but in other classes, even previous to this, math classes, physics classes, you've come across vectors before. So a majority of this, a good chunk of it, is going to be review. But I'm certain there's going to be some things that we go over that are going to be a new application of, vectors for you. So that's really the main subject that we have here. This evening, we're going to be looking at chapter 3. So we started in chapter 1, we went to chapter 4, and now we're kind of backing up a little bit to chapter 3. Again, the order that I feel like it's the way that I want to teach it. So I've got a PowerPoint presentation here on chapter 3. We do not go over every section in this chapter. It kind of has those two divisions where it shows how to calculate the problems or the solutions using math, okay, analytically we call it. And then they have graphical. We're going to stick to that graphical just like we've been doing, previously. So if you go through and like I say, I loosely say read the chapter, only the sections that we are going over in the PowerPoint and in class here are the ones that you're responsible for, as well as the examples. As we look at our session recordings, you're going to notice that I'll populate for this fall. We have the previous ones out there. So if you did want to, look ahead or something like that, you can always do that. And then Module 3 practice problems. This evening, we're going to do the first 4. That's vector addition and vector subtraction. Okay, so we'll be getting through those first 4 examples. The next time we're together, we'll finish up the last 2. Okay. And then our assignment. This evening, the content that we get through with those first 4 examples will take you all the way through up until the last 2 problems here. So the majority of the homework you actually can get started on after what we cover this evening. You'll also notice that there are the final answers out here for you. So you'll be able to check things, as you move on. So kind of like the same kind of thing. We will be using AutoCAD for all of our solutions. So this evening, that's what we'll be practicing in the practice problems and the examples that we go over. So what I encourage you to do is to open up the PowerPoint presentation. Also open up your book to page 43, which is chapter 3 in our textbook, and we'll get started. Okay, so at the beginning of the chapter here, it talks about quantities that we encounter in engineering and physics, and they usually break down into one of 2 categories. The first one being a scalar quantity, and I'm sure you've heard this terminology before, and a scalar quantity in general is any type of quantity that we deal with that can be fully defined with one thing, and that's called magnitude. So for instance, things like how long is something? It's 8 feet long. That's a scalar quantity. When we look at as far as temperature, how many degrees, how hot or cold something is, that's a scalar quantity. We can say it's 78 degrees and that's the temperature and that's fully defined. Time is another scalar quantity. Speed is a scalar quantity. If I look at my speedometer on my car and I just look down and I want to know how fast am I going, that's a scalar quantity. When I cross over into a vector quantity, I need 2 quantities, 2 things to fully define it, and that's both magnitude and direction. Now, I always have to ask, has anybody ever seen the movie Despicable Me? Most people have, okay? There's a villain, right? Do you remember the villain's name? One of the villains? His name's Vector. And he introduces himself and he thinks he's pretty cool. And he like slides over and he's like, "Hi, I'm Vector." And I guess as a mom, when I watched it with my kids years ago, and I taught physics at the other college I was at, and I also taught, this for many years. It was funnier to me because then he went on to say, "I have both magnitude and direction." And I think as a kid, it probably went over your head, but if you're somebody who knows a little bit about physics, it was kind of hilarious. So if you ever want to do a little YouTube search or just put Vector Despicable Me and you'll come across it. It's kind of cute and it is funny. So anyway, so a vector quantity is always going to be needing to be defined by direction and magnitude. Yes, it is. Yeah. He was And he has a squid launcher. That's right. Yeah, he invented that gun that he used. Yes. See, Brett, you're right there with me. So anyway, whenever I hear and I introduce vectors, I always just kind of crack up a little bit thinking about that scene from Despicable Me. So anyway, so vectors, we need two things to fully define them. We need both magnitude and direction, truly, just like vector. And if we look at a vector, you'll notice that we need to draw not only a line, but it's a line with an arrowhead, okay? So if we look here in figure 3.1, you're going to notice that we have a line going up at 30 degrees. It is measuring, or it's drawn at 1.5 units long. That just means that that's its magnitude. The magnitude we draw to scale, and it's going to be the length of the line on the vector. And then to complete it, to call it a vector, it has to have an arrowhead, okay? So a vector is not drawn as a line. Does everybody understand that? So every vector that you draw for me, which is going to be everything in chapter 3, you have to have an arrowhead on it. Okay, everybody understand that? Okay, so we're all on the same page. A vector needs an arrowhead. Do you understand? So I've said this about 4 times now. Vectors need arrowheads. Why do you think I'm saying that 4 times? Because inevitably I get an illustration with lines, and they're not vectors. So be sure that we're adding that for all of them. And the reason we need it is, remember, a vector is both magnitude, but it's the direction as well. Not only is the direction defined by, in this case, the angle of 30 degrees, but going up and to the right is very different than going down and to the left. So I need to know which side of the line is that arrowhead on. Okay, so that's why it's really important. Okay, let's go back over here. Now, when we draw our vectors, we're going to be drawing them to scale. So AutoCAD is going to be the tool that we use to be nice and accurate. So length, again, is going to be its magnitude, and then the angle is going to be the direction, along with the arrowhead for the vector. So the CAD knowledge that's required to graphically solve these vectors equations is going to be, first of all, drawing lines at specified lengths and angles. So we'll be practicing that in AutoCAD. You have that skill already. Inserting lines perpendicular to existing lines. That's going to come into play more when we start going to the next level and we talk about velocities. Extending existing lines, trimming them, drawing arcs, locating the intersections of lines and arcs, and then also measuring the lengths of existing lines with dimensions, and then also measuring angles with dimensions. Now, as I said earlier, we're going to be skipping over some of these sections. So we're going to go over to section 3.8 now, where it talks about graphical vector addition. Graphical vector addition. So graphical vector addition is going to be done with a method that we call tip to tail. Okay, and this is when we add 2 or more vectors together. So we have to have at least 2 of them to add together, but then we can add as many vectors as we need. Okay. So the process that we're going to take is basically we're going to draw the vectors in their orientation given in the problem, and then we're going to arrange them so that they literally are tip to tail. So we are going to position the tail of one vector on the tip of the previous one, and we continue to add those together. Once we do it, you're going to be like, ah, yes, I remember. Statics, we did vector additions like this. If you had me for statics, if you did, you remember this. Now, a resultant, also something that we covered in statics and at length, is going to be the one force that we can replace a number of forces with, and we have the same net effect on the body. So it's what we also refer to as the combined effect of vectors. Okay, so resultant many times is going to be signified by the letter capital R. We're also going to see some J's and K's in the examples that we do, but for the most part, resultant is an R. And then you'll notice here that in the vector equation that I have, you'll notice that we have A plus, then there's a greater than symbol, B plus greater than symbol, C. And in this case, that greater than symbol changes this operator from an algebraic addition to a vector addition. Okay. Now, if you're drawing this, for instance, manually, okay, so if I say R is equal to A plus B plus C, and it's a vector addition, a lot of times we're going to see the symbol of an arrowhead above the actual variable. But when we just have a keyboard we're working with or working in CAD, you could draw this if you wanted to above each one. But to be a little bit more efficient, we use the greater than symbol here in back of the operator. So that would be the greater than symbol, whether it's an addition in back of a positive value or an addition, the plus sign, or it could be in back of the subtraction symbol or the minus sign to be a vector subtraction. All that tells us is we cannot take the magnitudes and just simply add them together, because there's not only magnitude there, there's direction as well. So that's why we have to draw them out. Now, back in statics, we also did vector additions using the component method, right? That's considered an analytical. That's why I don't cover that in here, because we've had that before. So we're really just practicing the graphical solutions here in kinematics. The other point of this line right here is not only showing how we would symbolize a vector addition, but if we look at the quantities here, like assuming that A in each one of these is the same vector, B and C are the same vectors as well, we can add them in any order and we are still going to get the very same resultant. So whether I added A plus B plus C vectorially, I'm going to get the same answer for my resultant if I do it C plus B plus A or B plus A plus C. So if you're comparing your results to somebody and you notice you didn't do it in the same order, just look at the final result and see, did your resultant come out to the same number? And as long as it did, neither one of those is better than the other in order. Does that make sense to everybody? Okay. All right. So vector addition. So let's do a little practice on vector additions in the first couple examples that we have here. So our first example is going to be 3, 5. So 3, 5 is found on page 49. Page 49. I'm going to erase some of my notes I made earlier today. Okay. So page 49, example problem 3, 5. So it says here, graphically determine the combined effect of vector velocities A and B. What that means, combined effect, is find the resultant. Okay, that's what it wants to know. So find the one force that can replace these two and have the same net effect on the body. All right. So here's force A, 59 inches per second, going up and to the right. And I know that because I've got an arrowhead pointing up and to the right on the end of my line here. And I can see that it's at 30 degrees from horizontal. The other vector I have is going to be vector B. This is at 30 inches per second. And this is 60 degrees from horizontal. Now, the process we're going to take to add these two vectors together, I'm going to do it manually first underneath our camera here, but then we're going to translate that over to CAD. And why do you suppose we want to do this on CAD and not manually? It's a lot more accurate. Okay, we're going to get exact numbers when we use CAD. Okay, so that's why we're going to use that as our tool. So when we look at this problem, we know that our resultant is going to be equal to R. It's going to be equal to A plus B. Now these are vector quantities, and like I said, since we're going to be using CAD and we're going to be putting it as a keyboard, we are going to put the greater than symbol after our operator. So when we write the equation, and you will for all of these problems, you have to put the greater than symbol after the addition symbol to show that it's a vector addition, okay, not an algebraic addition. Now, our equal sign is what we call, what I refer to as the origin, okay? The origin is where everything starts. So we have to always draw an origin, okay? And as we look here, whatever order that you show your vectors to be added in is the order that you're going to draw them off of your origin. Since my origin, I like to say, is my equal sign, the first vector that I have is going to be vector A. So I'm going to look underneath here. My vector A is going to start, and it's going to be up and to the right at a magnitude of 59 inches per second at 30 degrees. So I would start the tail of vector A at the origin here, and it's going to be drawn up and to the right. I'm sketching right now, okay? It would be at a 30-degree angle from horizontal, and this would be vector A, okay? We are not going to dimension it at 59 inches per second. We're not going to show the 30 degrees. You're just going to draw it that way, but you are going to label it with the letter and make sure that the arrowhead is on it, okay? And it's to the correct length, so letter A. And the reason we're not going to do that is for each of the individuals, if we put a dimension and an angle for each one, there's just going to be too much information on there. We are going to add, for our resultant, the length and the angle, but not for the individuals that we were already given, but we have to have a label on them. Then we're going to add tip to tail, our next vector. So you'll know that we have vector B. This is 30 inches per second, and it's at a 60-degree angle from horizontal. So if I just kind of draw this in here like this, you're not going to be drawing that in there, but I just want to show you the orientation. My B is going to be something like this, okay? Vector B, and this would be like a 60-degree angle from horizontal on that side, okay? Now, notice that I took the tail of my B and I put it at the tip of the previous vector. So A started out at my origin, and then B's tail started at the tip of A. Now, I've exhausted all of my vectors on the right-hand side. So now I got to go over and do the resultant. So if I do that, I'm crossing over the equal sign. So that means I'm going to start my resultant, its tail, back at the origin. The equal sign is the origin. This side has to equal this side. So I'm gonna move my A underneath here. Okay. And now the tail of my resultant is going to start at the origin, and the tip is going to go to the tip of the last vector on the right-hand side. And this is going to be my resultant. Okay. When we draw our vector diagram here, we do not go in a circle, meaning I don't go A plus B and put the arrowhead for my resultant down at the bottom, because my resultant has to equal what this side was. This side ended right there. So my resultant has to have that same net effect. It has to end there. This is the one force that is going to replace those two individual forces and have the same net effect on the body. Okay, so this arrowhead has to end up pointing to the last arrowhead that we just created. Okay, now in this problem, it wants to know what is the magnitude and direction of our resultant. So the resultant, you are going to be adding a dimension to find the magnitude. Okay, and we'll do that in CAD. You additionally are going to have to determine what is the angle from horizontal or vertical that it's going to be, not from another vector. And I'll continue to reinforce that as we go. So magnitude and direction. So that's kind of the process we're going to go through. Let's make it exact and make sure that we get the same answer that's in the book. So I'm going to go over to AutoCAD, and I am going to start with my Kinematics start file. I have the inches one open. Doesn't really matter which one you have open. I'm going to do a rename right away, save as, and this is going to be example 3.5. Now, this particular vector A and vector B, vector A is at 59 units long. Yes, it's inches per second, but we can't change our units to inches per second. And like I said, it's basically units long is all that I'm worried about. All right. So I'm going to draw it at 59 long at a 30-degree angle. So I'm going to go back to AutoCAD here. I'm going to switch to my object line layer. I'm going to start the line command. Now, I am going to start with just a left click. I'm going to put my line weights on and turn my ortho off. And I know that from the point that I just created, or relative to that point, that means I have to enter the coordinates, I have to use the @ symbol relative to the last point. And the length of this is going to be 59 long. And then I have to tab to get the angle. This angle is from 0 degrees, standard 0 degrees, which is horizontal, okay? And if I move in a counterclockwise direction that is positive, Clockwise is negative. So if I go back underneath here, right here is standard 0 degrees. So 30 degrees going in that direction up to that line is counterclockwise. That's a positive direction, okay? So if I was going down clockwise, that's a negative direction. Does that kind of ring a bell from when we did this stuff in AutoCAD? So if I go back over here, the angle that I want to put in is 30 degrees, a positive 30 degrees. Okay. Then I'm going to hit escape and I'm going to do a zoom extents. Okay. Or Z, enter, E, enter. And this is the length of my vector. Okay. Now to put my arrowheads on here, we're going to keep it very simple. I'm going to do the line command again. At the end point of the line, I'm going to simply draw 2 lines and make it look like an arrowhead. That's it. We're not filling it in. We're not doing anything else. Remember, this is for layout purposes only and for getting an end result of a resultant, okay? So I don't want you messing around with leaders and trying to put those in position. You could, but then you're worrying about scale and the size of them. All I want to see is if this is going up and to the left or up and to the right or down and to the left, okay? All right. Then what we're going to do is we have these letters down here, right? So I'm going to move A and I'm going to put it, I don't know, right about here. It's pretty small. If I would do a screenshot of this right now, I wouldn't see the A. So I need to scale that up. So I'm going to go to my modify section here where scale is. I'm going to select that letter A, hit enter. I'm going to select, I don't know, right by it. And I'm going to move my cursor away from it. And it's going to make it larger, right? I'm not entering a scale factor. I don't even know what the scale, it says it's like 12 something or 12 and a half or so. But I want to make it big enough so that when it is next to my vector, I'm going to move it next to my vector, that it's in the right place. I think I'm going to put A underneath it, like right about there. Okay. So that's A. It's 59 units long and it's at 30 degrees from horizontal in a counterclockwise direction, right? Now I'm going to do the same thing for B. I'm going to draw it just like I see it here, 30 units long. Now this time, this is at a 60 degree from 180. So how AutoCAD works when I put those degrees in there, it starts from a 0 degree standard. So this is going to be what? It's not going to be 60 degrees.
120.
If I go from 0 here, this would be 180 back to here. 180 minus 60 is what? 120. So this is going to be 120 degrees counterclockwise. You see that? So if I go back to AutoCAD here, I start the line command. I click first. Remember, you need to use the @ symbol. Otherwise, it's not going to be a relative coordinate. It is going to go from absolute and then it's not going to be right. You have to go from the point that you just created. So @ symbol, it's going to be at 30, tab, and 120. Okay. And then there is the length of my vector B. And now I'm going to add in my arrowheads. And again, this is just 2 lines showing that, okay? We don't need to make a triangle and fill them in or anything like that. Then I'm going to copy my scaled A over. And I'm going to put and change that to capital B. Okay. And then the other items that I have down here from my start file, I can erase those. Okay. Now, the next thing I'm going to do, I'm going to copy my A again. And I am going to, I don't know, somewhere down here. I'm going to double click on this and I'm going to write my vector equation. My vector equation is going to be R is equal to A plus vectorially B. So capital R is equal to A and then plus greater than sign B. Okay. You have to have the greater than sign in there because that lets me know that it's a vector addition and not an algebraic addition. If I don't see that in there, points off. Okay. So now I want to add these 2 vectors together. If I look on the right-hand side of my equation, I'm starting with A. So that means that A is going to be at the origin. Okay. So I have A in position right here. And I can leave it just like that. All I need to do is add an origin. To do that, I am just going to add my horizontal and vertical lines. So something like this. It needs to be kind of like the standard crosshairs. Now, you don't have to, have them all the same length, something relative. And it has to be a large enough origin that I can see it when you do your screenshot. If you say to me, it's there, but it's too small, points off. Okay, I need to see your origin because I need to know if you did it in the right order. Okay. So equal sign, origin, A is first. All right, so the tail of A is going to start at the origin and the tip is going to go up and to the right. Then to that, I'm going to add vector B. So I'm going to do a move. I'm going to put a window around B, enter, and I'm going to select the tail of B, and I'm going to place it at the tip of A, tip to tail method. Okay. And I keep it in the same orientation that I drew the original in. So now what I've done is on the right-hand side of my equal sign, I have everything done. If I would have more vectors, I'd continue to add them, okay, and place them at the tip of the previous vector. Now what I'm going to do is I'm going to go back to across the equal sign, so back to the origin, and I need to draw my resultant. So I'm going to change my object 2 layer. And I'm going to put a line from the origin to the endpoint, the tip of vector B. Okay. Now, the arrowhead, remember, is going to point at the tip of the last vector. So my arrowhead for my resultant is going to be going up and to the right. So I'm going to zoom in here a little bit. And the arrowhead that I'm going to create is just going to be simple, line at the endpoint. Now I make it a little bit bigger so it's obvious which is the arrowhead for it. Okay. I'm gonna do a quick save. Now I'm gonna copy one of the letters, either B or A, and I'm gonna move it right there. And I'm going to rename this capital R for resultant. Okay. So notice no dimensions on A or B. They're fully defined from the problem. So I drew them to their size. I just have to label each one appropriately, A and B. But the resultant, I need to label it, put an arrowhead on it, and then I need to change to my notes and or dimension layer. And I'm going to put an aligned dimension to find the length. So I'm going to need to go from endpoint to endpoint. And you're going to notice that I can't see the number, right? So to be able to see the number, you have to go to the annotate tab, the down arrow for the dimension. Our dialog box comes up for the style manager, modify, and we're going to go to the fit tab. Down at the fit tab here, the overall scale, we want to change it from 1 to about, I think 25. We'll see. So you just pick a number. And I'm gonna say set as current, close, and we'll see. That looks pretty good. Okay. If you have to play around with it, it doesn't have to be the same perfect size as the other fonts, but it has to be large enough when you do the screen save or the screenshot that I can make out the number. Okay. If I can't make it out, when I try to zoom in on a PDF or the version of it, the screenshot, it just gets blurrier, okay? It doesn't get any clearer. So that's why it's important that you make it large enough so that I can see it. Now I've got magnitude. I've got the resultant labeled. What else do I need? I need the angle. So to get the angle, I go back to the home, arrow down. I'm going to do an angle dimension. This angle has to be from the horizontal axis or the vertical axis. You do not measure to another vector, okay? It has to be from a horizontal or a vertical. It's the only place it can be from. So I'm going to go from the horizontal axis to my resultant. And if I pull this out, there's my 57 degrees, okay? So I've got a magnitude of about 66. I think it's inches per second, and then my angle is 57. So if I go back under, let's check our answer. Down here, if you would, are the screenshots that the book came up with. So for the magnitude, they have a magnitude of 66, which we got. And the angle to that resultant is 57 degrees. They added the angles for the individual A and B vectors. I really prefer you not to do that, okay? So if we look back over here, we only want the magnitude, direction for what you're solving for. Don't add it for A and B. It's just going to add stuff that we're just not interested in. You also need to make sure that you have your equation for this vector addition. So R is equal to A plus vectorially B. Every one of the vectors here needs an arrowhead. Every vector needs a label, okay? And make sure that you make your resultant different than the other ones. It just stands out because that's their final answer, okay? Also, make sure you have an origin that is seeable. So now what you're going to do is this is going to be the screenshot for your first problem, example 3.5 in your module 3 practice problems, okay? So questions on this example right now. Okay, this is one of the things that should be familiar to you at this point, because I know you did it in statics if you had that already, and most of you have had that, or you would have done it in physics for sure. So I'm going to stop our recording here, and then we'll start our next example on the next recording.